Last lecture we were taking a look at the process of software reuse. We looked at what exactly is reuse and what are the different factors that affect reuse, what are the benefits and disadvantages of software reuse, and we saw that the main benefits to be accrued from reusing software at various levels. The first one was that of reliability. So the components or the COT software that you're reusing essentially would have been well tested in previous situations, possibly previous production situations, and the bugs would have been ironed out. So the problems would have been fixed. So the degree of reliability you get by reusing such a component is fairly high. We also saw that there was reduced process risk because of the fact of reuse. So you don't have to get involved in that much more of the estimation process, given that this component already exists and can simply be reused as is in the current project. And an obvious byproduct of the whole thing is accelerated development. So you can do rapid application development with components by stringing them together and just providing the glue between these components. And certainly the compliance to standards may come for free, because largely components that are meant to be reused or COT software or frameworks that are meant to be reused are typically those that adhere to certain standards. So the level of compliance to these standards within your own software goes up by that much. The disadvantages of reuse clearly are that evolution of your software may not be as simple, so maintenance becomes much more expensive because of the fact that the components that are in there may not evolve along the direction that the application which is made up of these components is evolving. Certainly there's also the issue of the not invented here syndrome, where programmers would like to primarily develop their own software. So it's not as much of a disadvantage as it is a factor that affects reuse, and it's unfortunately very few standards have emerged for the construction of such component libraries worldwide that you can then go and search for when you want a particular component. So finding and adapting these components may not be as simple a task as maybe even developing your own component in some cases. So these are the advantages and the disadvantages of reuse. When we saw various levels of reuse that could be done, and we were into the discussion of component based reuse, the first one was the program generators or the application generators, and these helped us reuse entire algorithms. The second one was the component based reuse, where a component was a set of related interfaces, a set of related objects that were strung together, could be treated as a single unit that provided some piece of functionality. And different abstractions for components, certainly there were the functional abstraction, the data abstraction, and so on. Finally, we were beginning to look at application frameworks. So there are three other levels of reuse that we have not considered, which is what we are going to essentially do in the rest of the lecture today. And the three levels of reuse are the reuse with application frameworks, and we'll go into a little bit about what application frameworks are, what is the criteria for selecting application frameworks, and so on. Then there are product line architectures or COTS, off the shelf systems, and reuse based on these systems. And finally, we'll take a brief look at design patterns, which helps us achieve a design level of reuse. So what exactly are application frameworks? We briefly studied this in the last class, but application frameworks are essentially the skeleton of an application, right? So it has the infrastructure, it has the scaffolding necessary to build an application, but it is not an entire application by itself, primarily because of the fact that two or three things have to be done. The framework would have to be customized to meet the needs of that particular application development scenario. So for example, ORB or ORB may be a middleware level application framework that allows you to build distributed object applications. What it gives you are certain features such as communication, it gives you the features such as object persistence, transactional reliability, and so on and so forth. But still, by itself, an ORB is not an application. You have to put the necessary business logic in there for you to create the application. At the same time, things like the Microsoft Foundation classes is an application framework that helps you build UIs and so on. So it can be considered to be the skeleton of an application design that has to be customized, and it has a certain number of abstract classes within it, or a certain number of abstract components that have to be concretized. So you have to derive, extend, and produce the code for these abstract components, only then will it become a live application at this point in time. So, there are different classes of application frameworks. The lowest level application frameworks are those that provide communication operational system features, right. So, it may provide user interface, it may provide compilers. So, you can generate a compiler out of a certain set of classes that exist. So, these are called system infrastructure frameworks. The second and an example of this is what is called ACE, or the Adaptive Communication Toolkit that came out of San Diego. Then there is the middleware integration frameworks, which are primarily the ORBs, as they call them, the object request brokers, or the container architectures that have become very popular today for the construction of enterprise applications. And these are basically server side, essentially server side containers, standards and infrastructure that help you to build applications on top of this. So, for example, there may be a messaging framework that will allow you to send messages asynchronously to somebody else, for the other person to receive messages from a particular message queue and so on. So, the plumbing is all provided in these kinds of frameworks, but you still have to write the specific messages that have to get delivered, and the processing of these messages is purely your application specific code that has to be written out for this. So, finally, there are the enterprise application frameworks that basically support the development of enterprise applications such as telecommunications. There may be vertical applications that are targeted towards a specific vertical domain, such as that of telecommunications, such as that of manufacturing, such as that of logistics planning and so on. Or these can be generic as well. So, there can be two layers, if you will. Generic application frameworks may be examples of these are things like Apple's Next Step. So, these are kind of like middleware integration frameworks. They give you all the functionality that is required to put together enterprise applications, or they may be very specific to a domain. So, if you take a look at OMG and Corba, there are application frameworks around Corba to support the construction of telecommunication applications only, or it can be something like Rosetta.net for the chip industry or the semiconductor industry, which was basically a framework for B2B integration of the people involved in the semiconductor manufacturing process. So, frameworks, like we said, are fairly generic and they have to be extended in order for them to actually prove useful. The extension has to be done in one of two ways. The first method by which frameworks have to be extended would be to make certain abstract components or classes that exist in the framework become concrete. So, you have to plug in specific code to instantiate certain object types that are specific to that application. That is one thing. The second one is typically there are events that the framework will end up receiving, and the events would be passed on to the application code for the application code to act upon. An example of this would be a network management or a monitoring framework, in which the event that is coming off the network may say that this particular network segment is down. Now, the framework knows that this event is coming off, but it does not know necessarily what you want to do with it. So, depending on whether you are building a monitoring system or whether you are building some kind of a management system that is actually going to take action on this, you might treat this event differently. So, what you will have to do would be to actually write the code that does the processing of the event in this particular case. And so, the code would be written that is called by the framework in response to some event occurring. So, this is the other form of extension that you would likely have to do. One of the common problems that are obviously faced is that in order to do these kinds of extensions, you have to understand the framework pretty well. You have to understand the class hierarchies within the frameworks, you have to understand the responsibilities of the different modules within the framework and how they interact with each other. So, the level of complexity may be quite high when you are dealing with frameworks. Now, there may be several frameworks out there. The question that might come to mind is, how do you evaluate such frameworks in order to make a decision as to which framework to go with, or whether you go with the framework at all. And here are some of the criteria that you can use to evaluate these frameworks. Obviously, the different operating platforms that are supported, does it run on Linux, does it run on Macintoshes, does it run on Windows machines, and so on and so forth. The different programming languages that are used. The framework is obviously specific to a programming language, unlike a design pattern, as we shall see later, which is merely an abstract notion of design that can be instantiated in any programming language. So in this case, you might be looking for things that are only based in Java or based in C++, or some mixture of the two, C# and so on. The number of standards that it is adherent to, is it only based on standards, or is it purely compliant? It is compliant with a fairly high degree of reliability on these standards. So that's the question that you have to ask yourself. And one of the reasons why you ask yourself this question is because you may want to extend this framework, you may want to integrate this framework with other frameworks, other applications, and you will not have this integration capability unless it's compliant with the standard. Certainly the vendor support, the simplicity of the framework, the performance of the framework, the reliability of the framework, and its suitability for the task at hand. We can actually take a look at some of these criteria in greater detail. So some of the 5 to 6 criteria is what we'll look at today. So the maturity of the framework is probably the single most important factor, assuming that it is suitable and so on. And by maturity, what we mean is, has this been down several release cycles already, or is the very first release of this framework that is coming out? First release products, first release frameworks could have a lot of bugs that you will have to watch out for. These haven't been ironed out because they haven't been put through the paces in some kind of production applications. For a strong framework is something that is pretty mature, it has been through several release cycles, and it has been used in several large production applications. Other end of the scale is really weak frameworks in the area of maturity, where it's typically their first release. It may be used by some dot releases might have occurred, it may have been used by such small applications only. So extensibility of the framework is pretty critical, because it would, more often than not, it would be the case that you would have to add some capability. The framework will not provide 100% of the capability. So extensibility would imply that it has solid documentation, its adherence to standards, well-known standards that you are familiar with. It may have a search engine for API, so instead of sitting and digging through reams and reams of paper, you will have some kind of online search capabilities to figure out the API that you need to work with, and so on. And at the weak end of the scale, there is no documentation at all. It's some kind of a template system that only gives you a very small degree of flexibility as far as customization is concerned. Integratability of the framework is its ability to work with other applications easily, or make it work with other applications quite easily. Again, this depends on standards. It would also depend on what are called adapters. Adapters are bridges that are built between a particular framework and specific application. So for example, there may be a bridge to the IBM NQ series from this particular framework. This would mean that it will work well with the IBM MQ series of products. There may be a bridge to a specific database, say Oracle or Sybase or something like that. Web readiness is something that is being asked of more and more today. Obviously, the strong end of the scale would imply that this is completely web ready. It can be also, any extensions that are made can be web enabled pretty easily. At the weak end of the scale, it has a proprietary UI, probably written in C++ or something like that, and you would need that UI to be installed for this application to run. Platform independence is obviously a fairly critical feature that you would look for. So it can range all the way from already platform independent, so it works on Java, some kind of a virtual machine, or the other end of the scale, it's completely tied into a specific platform, and a significant amount of code would have to be rewritten if this had to be ported onto another platform. Scalability is another feature, and finally the workflow management metaphor. Does it have a workflow engine that is in there? Does it have any kind of capabilities to graphically define workflow and business processes to this, and then subsequently these things can get automated. So these are some of the criteria for evaluating the suitability of frameworks. And are frameworks the best form of reuse? It's hard to say. Frameworks certainly provide a higher granularity of reuse compared to components, but that can also be a disadvantage in terms of when you're extending the system and the framework doesn't support it. Now you might be in a fair bit of trouble at this point in time. So it depends on how extensible it is and how you can integrate this with other components and additional frameworks and applications. Also, the degree of understanding that you would have to achieve in order to make this framework approach succeed would have to be quite high. So you would have to get into the guts of the framework and understand exactly what these interfaces do, exactly what are the interconnections between these different interfaces, because your extension capability depends on that understanding at the end of the day. So the next level of reuse that we're going to talk about is what's called COTS product reuse. COTS stands for common off the shelf. So common off the shelf products are essentially entire systems or applications that have been built that you're going to reuse in certain scenarios. COTS systems usually offer some kind of an API, but you may and this API would be used for integrating the system along with other systems. So for example, if you are building a ERP system for your business, you can choose to buy an SAP like framework. This is a framework, and you have to basically customize SAP for it to work in this case. Or you may choose to buy a pre-built application like White Plains or something like this, which is a complete application in itself. So it has the UIs, it has the database schema. All you have to do is to start populating data into this application. It's going to work. So this is obviously a much higher level of reuse, but it is relevant in situations where you're building very large systems, right? It's not really very relevant in building small things. So for example, you're a brand new business and you wish to set up an ERP system for your company. You're a brand new business, you wish to set up an e-commerce web portal for your company. Now this would mean that there's no point developing these from scratch. Certainly there is some benefit to be gained from using frameworks and then customizing them, but these things have become so common, been used so many times now, that you might as well buy an application that has been pre-built completely and just maybe customize the look and feel of this, brand it appropriately for your company, and just run it as a portal, because it may not form a very important part of your company's strategy at the end of the day. There are different integration approaches that can be taken when you use common off-the-shelf systems or products. The first one is the database approach, in which all the operational data is stored in a single central database, and all the different applications now will have to access the single central database. This may be a little difficult because it assumes that this database schema that you're going to have is something that is accessible by this common off-the-shelf application, which may or may not be possible. The second one is what is called the blackboard approach. In the blackboard approach, the data sharing amongst components is basically opportunistic. This means that it is there's some kind of a middle tier messaging layer, say a publish subscribe mechanism, which can be used for data sharing. So a system that is going to write data is going to publish data, and any of the system that is interested in this type of data is going to pick it up. So an example could be that instead of integrating an order management system and a billing system, but directly allowing them to talk to each other, you can allow them to talk through a publish subscribe bus. So the order management system is going to publish the fact that a new order has arrived, the billing system may pick it up, the inventory system may pick it up, and there could be other systems within the company, logistics, planning system, shipping system, etc., which pick up the fact that this new order has arrived and prepare to complete the order. All of them do their tasks in turn. And finally, the object request broker strategy is one in which two applications directly talk to each other. This is not publish subscribe, this is not asynchronous messaging, but this is synchronous application to application contact that is going to happen. So these are some of the different integration approaches which become very important when you are talking of multiple applications that you are reusing whole and then integrating or tying them together in order to provide the functionality required by your business. So some of the examples of COTS reuse, I think the most significant example is the second one on the slide, which is Boeing's new 777 aircraft, which basically had almost 4 million lines of pre-written COTS code. So these are entire applications that were picked up and integrated into running of this airplane. So this is a very good example, largely used in other defense projects and so on. Some of the problems that you are likely to run into with COTS approaches are lack of control over the functionality is the first problem. Because it is an entire application, the granularity at which you are doing the reuse is very high. It's a very high granularity of reuse. So there may be out of the 10 features that the system provides, you may need 4, but you may not need the other 6. That's one level of it. So it's a superset of the features that you require. The second situation, which may be far worse, is that it may have 10 of the 12 features that you want, but the 2 other features are not there, right? So you don't have control over the amount or the functionality that you're getting in here, because it's a system. You have to pick the system as a whole. You can't pick and choose the features of the system. right? The same thing with performance. Unless it meets the performance needs, which it may for some functions and may not for some functions, then again it requires a lot of customization, a lot of extension, and a lot of recoding in order to get this thing to work right. Certainly there could be problems in interoperability, the same problem as we saw with frameworks, but here interoperability becomes much more key, because it's likely that there are multiple applications working in a single scenario. In the case of frameworks, it may be that the framework underlies all the applications, and so interoperability may not be that big a deal. Unless they are really conformant with standards, well-known standards, well-established standards, it may be really difficult to integrate these things. But the development of technology such as web services and so on has allowed us to basically wrapper some of these applications with standard interfaces so that they are now able to talk to one another. The same problem with system evolution, as you would see with component-based reuse and with frameworks, is that every time your system needs to evolve, the CORD system should be capable of scaling up and evolving in the same way or sense. Otherwise, this could become a real problem, right? And the support always is going to come from vendors, so you are not controlling your own destiny in this case, and you have to be careful when you are reusing entire systems that the vendor is going to be around in the next 5 years. For example, when your system is going to be around, if they go out of business and there's nobody to support you, then how are you going to manage the maintenance and the evolution of your system is a situation that you would have to keep under control. So one of the things that we would like to come back to is we saw the notion of reuse with components earlier. One of the topics that we wanted to close out on that is how do you create components to be reused, right? Remember earlier we saw that there were two paradigms here, design with reuse and design for reuse, and in this case we would like to take a look at specifically in the case of components, because components are essentially things that you create, are units, encapsulated units of functionality that are meant to be reused in the first place. So we would like to take a look at how do you make a component become more reusable. So there is no such thing, it's not a black and white, it's not a boolean saying this is reusable and this is not. And typically the degree of reusability depends on how well designed this component is, right? So let's take a look at what it takes for us to make a component become reusable in the future. So that typically the general strategy that is used is generalization, right? So you would take a component that was built for a specific purpose, but you would generalize, you would raise the level of abstraction and generalize so that this can be used in multiple situations with the API that you are going to provide the component. So the component reusability features are that it should reflect stable domain abstractions. What does this mean? So if there is some feature in the domain that this component is representing, let's say if you are in the network management domain, it may be representing a MIB, which is a management information base for a network device. Now the notion of a MIB is very standard. The notion of interfaces to the MIB are well established. There are SNMP standards that have existed since decades. So there is a certain stability in the domain as far as a MIB is concerned, right? But if you take a look, for example, at the Java Management Extensions API, which are now slowly beginning to penetrate the network management domain, it's not very stable. It's very new, it's very experimental in nature, and it's something that keeps changing. So what we want is really the component should reflect a fairly stable domain abstraction. That's when the component will live and will not change by itself every time the domain abstraction changes. It should hide the state representation. The only thing that you want out of a component is what it is capable of doing, not how it is going to do it. So this is the standard principle of object orientation that we extend into this scenario, right? It should be as independent as possible. So remember, a component is characterized by the interfaces that it depends on and the interfaces that it provides. And the number of interfaces that it depends on should be as minimal as possible, otherwise this is not a very reusable component, because every time you bring this component in, you would have to make sure that the other interfaces were available, so you might have to bring in a whole host of other components to support it. And finally, it should publish all the exceptions that can occur through the component interface. This is very important because there may be situations the component is not able to handle. Unless it lets you know that this is exactly what happened and I can't handle the situation, you will not be able to take evasive, corrective, whatever kind of action you need to take at that point in time. So the exceptions have to be well published as part of the components interface also. Certainly there will exist a certain trade-off. When you start making components be more reusable, you're tending to be becoming more generic. So whereas the component in the first case could have done with say 4 or 5 methods or 4 or 5 functions that it performed, now to make it be more generic you might have to add another 5 or 6 functions. So now the usability of the component, because it has 10 or 12 functions, so the understandability and the usability of the component goes down, but it is certainly far more generic. It is applicable in a variety of situations in this case. So that is the trade-off that you would have to make. The trade-off is that you make it more generic, you make it more reusable, but the degree of usability starts coming down at that point in time, because it is that much harder to understand the component interfaces now, right. So this is something that you have to keep in mind going forward. The cost is certainly something that is to be borne in mind, and because the cost of developing a reusable component is significantly higher than the cost of developing a specific equivalent. But what we mean by this is that if you are developing a component or a module just for that one application alone, right, suppose you are developing a widget for taking in text input in a UI, is a good example of a component, right. The widget might, if it were being written in a very specific manner for that particular application, maybe that application only required 2 lines of input, for example, and you're restricting it to 2 lines of input at this point in time. But this is a specificity, this is a specific feature that when you want to make this generic, you need to certainly allow for a customization of the number of lines of input that can be accepted by this particular text input box widget, right. So you're making this more complicated, but for a reason, so that it can be reused across multiple scenarios. Now this comes at a cost. So you have to add the configuration interfaces to this, you have to test the configuration interfaces, and all this is going to cost both in terms of time and in terms of money, right. So this how this cost gets absorbed, does it get absorbed as cost of the project, or does it get absorbed as part of the organizational cost that cuts across multiple projects, because this component is now reusable across multiple projects, is something that you have to keep in mind. And if there is the right encouragement within the organization to develop reusable components, then this will be a successful project going forward. Else typically reuse and design for reuse is likely to fail. So what are the kind of enhancements that would have to be made to components in order to make them be reusable going forward, is the question that you would like to ask yourself. We talked about generalization is the key strategy that is to be adopted when you make the component reusable. So what are the different types of generalization that can be done, and what are the details of these? So the first one is generalization of names, right. Names in a component can be modified so that they are not a direct reflection of the specific application entity. What this means is that in the case of a text box, let's say the application that was being developed was a telecommunications application. A telecommunications application for a particular company, for a particular department, had this widget that you are developing, the text box input widget. Now if you name the widget as something that is very specific to that application because it belongs to part of that application's package, then it loses some of the genericity. So you might just want to name it a text box widget, and you may provide an inheritance hierarchy that is completely generic in nature. It shouldn't be inheriting, it shouldn't be, so anything along the path, the naming path that it contains should not be specific to that particular application, right. That's the first thing. The second one is one of operational generalization. So this can be done in 2 ways. One is specific operational interfaces, right, can be extended to make it be more generic. So for example, if you were taking in, let's say, 2 parameters to a specific operation, and in order to make this operation be generic, you might want to take in a 3rd parameter which always defaults to a particular case as far as your application is concerned. So that's the strategy to deal with it, is that you add a 3rd parameter, but you add a default value for the 3rd parameter, so that when it is not specified, the application the component always assumes a default. And that way you have provided for a generic scenario which can be used by multiple people, but that specific application for which it is being developed does not need to have the overhead of specifying the third parameter every time it is going to use the component, right. So that's one dimension along which operational generalization can be done. The second dimension is one of adding different operations. So the example that we talked about earlier was that of a list or a stack. So instead of creating a specific list structure that is only going to be used for that particular application, you can create an abstract data type, which can be a linked list data type or a doubly linked list data type, right. And this may need many more operations that that can be used in different scenarios. A good example could be that let's assume that in your application you are always going to append to the end of the list. There was no question of inserting into the middle of the list. So you really didn't need a function call to say insert into the list at position n. But in the case that you want this to be a generic component, you certainly want a function call that says insert into the list at position n. Also you want another call that says append to the list, that is insert at the end of the list, right. So here is an example of operational generalization where you want to add certain methods. So you may also need to have some methods for initialization, specific kinds of initialization that can be done. So multiple constructors might have to be provided to an object interface. Different ways of dealing with destruction of that component would have to be provided, cleaning up that component would have to be provided, and so on and so forth. The third one is the exception generalization. So here many more exceptions that could occur in different scenarios might have to be added, right. So for example, a component is to be used only in a local access method, or it can be used remotely accessed from some place, right. So if you want to make this a generic component, you obviously need to add exceptions that deal with remote communication exceptions that may occur on the network, because now the component can be accessed remotely, which means it can be accessed in a distributed manner over the network. So to increase the robustness of the component, to increase the situations that this component can handle, you essentially have to make sure that application specific exceptions are removed and exceptions that are fairly generic, and the exception management is taken is paid enough attention to increase the robustness of the component. Finally, one of the reusability enhancement features, this is not really a generalization feature, this has to do with reusability enhancement in general, is that there can be a process of certification, right. So for example, if you are providing Corba components, if you are providing components that adhere to the Corba standard, then you might want to have it certified by OMG, which is the organization that deals with the Corba standard, right. So component certification could be fairly important, because it will also give a certain level of trust to the user of this component, saying, oh, it has been certified by Sun, it has been certified by this authority, and I can therefore safely use the component in my application, knowing that it has met certain quality standards, it is fairly robust, it's not going to destroy my application going forward, and so on and so forth. There might be vendor support that is possible with this, and so on and so forth. So that's something that has to be kept in mind as well. So what is the reusability enhancement process itself look like? So what we have seen so far essentially is that components can be built for reuse, and component applications can be built by reusing components. So what we're discussing here is the process of reusability, is the process of increasing the reusability of the component itself. Earlier we had also seen a similar process which dealt with reusability within the software engineering life cycle. How do you account for reusability within your application development life cycle? Now let's take a look at the reusability enhancement process. So the first thing is that you have an initial component interface that you start from, right? So you've built a component, and what you need to do is to make this be a generic component. The component you have built may have been for a specific project. So the first thing that you have to apply is the name generalization process. So there are plenty of people, for example, whose names include that of the package for which it is being built, whose names reflect the company for which the code is being built, whose names reflect the application, and so on. So you should try and stay away from that as far as possible. So name generalization is the first thing that is done as part of this process. The second one is operational generalization. And operational generalization, as we have seen before, can take two different forms. The first form is that of adding methods. By method, we are referring to an object oriented term. Adding interfaces would be a better way of describing it. One is a specific interface is genericized. So these are the two different ways of doing operational generalization. So the next thing you may have to think about is the exception generalization. We've already seen these three things: the name generalization, the operational generalization, and the exception generalization processes. Once you pass these steps, one of the things that you would have to then do is to significantly improve the documentation of the component, because if it is a component that you are going to use purely within your own project and you have written the component, then you probably don't need a whole lot of documentation. But on the other hand, if somebody else is going to use this component, then they would need a lot of documentation, because they may not necessarily understand your intent when you develop the component. Right. Finally, it has to go through a certification step which will check all of the above. Is it generic enough? Does it have good documentation? Is it robust enough? Does it pass all the tests that it says that it is going to pass, and so on? And at the end of this process, then is going to come a reusable component. Right. A good example of this might simply be data types. The string data type, for example, started off as a fairly minimal interface, but then as things went along, people realized that this was a very, very useful data type to have, and a lot of functions were now added to the string data type, and the final form in which you see the string data type is nothing like what it used to be when people started working on it. However, it is very, very useful in a very wide variety of situations. It has quite a few interfaces to it. Obviously could be the source of some degree of confusion, but at the same time its usefulness overcomes that confusion, because of the fact that it's usable in such a wide variety of situations. So some of the generalization techniques, and these are specific techniques that we have come up with. The first one is to identify design decisions that may be abstracted, parameterized, or otherwise undone. Identify dependencies or commitments to remove. Right. So anything that is a dependency that the component has on other components must be removed as far as possible. You want this to be independent. Any hardwired external dependencies is what this talks about. Make it parameterized. So parametric context can be added. This can be user defined, and parameterized dependencies can then be created if you need it to be. Then large effect operations on objects with well defined set of small effect operations should be done. This basically says that if there is a single method or single interface that does a lot of things within the component, you should try and replace this with a set of smaller interfaces which do a smaller amount of things. So for example, there could be one interface on a list that says append to the list and increase the count of the elements in the list, and so on and so forth. But it could be replaced by two single operations, one that increases the count of elements in the list and one that just appends the particular item that is being added to the list. So that's because the understandability of individual operations goes up significantly, and therefore the understandability of the component as a whole goes up as well. Always write components that have customizable behavior for error conditions. This is the notion of exceptions, writing a lot of exceptions within the interface of the component, and making sure that if you cannot handle certain situations, then there is a well defined exception that is going to go back up, it is going to ripple up, and the user of the component can take evasive or the corrective action on that particular exception as well, right. And the last tip here is to generalize from several instances. If you the first time you are writing a component, if you say, oh, I can make this generic, and immediately go ahead and create a reusable component out of that, it is likely that the situations for reuse, the potential for reuse may not even exist. So, but if on the other hand, if you find out that we are using a similar component over and over again in a particular project or across different projects, that is the time to actually create a component out of it, a reusable component out of it. So, don't generalize it on the first try. Always wait for empirical evidence that this component is indeed going to be useful across multiple situations, and when you run across 2 or 3 such situations, that is the time to make this a truly reusable component. The other important thing about reusability is to generate a good mental model about the component, right. So, the client or the person who is going to use this component in the construction of another application needs to have a good feel for the component. That is the only time they are going to reuse it. And here are some guidelines for creating good mental models of components as well. So, specifications have to be very well written for the components. So, if you are just giving a bunch of interfaces with no notion as to what the expected behavior of these interfaces is, that is not a complete specification. Remember, in the lecture on formal specifications, we took a look at what were called abstract data types, and abstract data types contained a section of behavioral specification within it, which came in the form of axiomatic specifications. So, you specified a list of axioms that said that the method interfaces that I am providing in this component or data type have certain rules that they will follow, and here are the rules in the form of axiomatic specification. So, if that something like that exists, it will give the appropriate mental model in terms of how does this component behave when I use it, right. It is not merely the interfaces. Also look at visual representations, right. For modeling the states of object, choose models that can be drawn visually. So, UML state models, for example, can be used in this case. Writing formal specifications is a very good idea. It both gives the user the confidence that this component has been well thought of and is going to behave robustly. Also, it gives them a very good idea of how this component is going to, what is the behavior, expected behavior if I use this particular interface of the component, and so on. So, here are some clues for generating good mental models. Write programs that display model like values, object representations, and allow exercising of all operations in the specification. So, interactive sessions is always useful to actually do this, and intermediate levels of specifications between a raw specification and an abstraction is something that is also obviously quite useful to do this. So, that is the process of developing reusable components. We are going to move on to the next level of reuse. So, we kind of had a small break in this talk on reuse, where we started out by explaining different levels of reuse. We took a look at component based reuse, we took a look at program generators, which is algorithmic reuse, component based reuse, then we looked at frameworks, and then we diverted a little bit to take a look at how do you create reusable components, not just how do you build applications by reusing components. And now we come back to the next level of reuse, which is that of application families or product line architectures, as they call them. An application family or a product line is basically a set of applications that drive off of a common core. So, for example, it could be driving off of a middleware framework, for example, or it could be something much more specific than that. So, if you take a look at a bunch of ERP applications, which may be shipping and receiving and purchasing and asset tracking and logistics, and so on, all of these are kind of related applications. They all belong to the domain of enterprise resource planning or enterprise resource management. So, they can work off of a common database, they can work off of common business flows, for example, which can be reused across these applications, and so on. So, that is what is called a product line or an application family. and the common core of all of these is reused every time a new application is added to this family. And then obviously the application that is added is specialized in some way, right. So, different kinds of specialization can be done here. So, platform specialization can be done. So, different versions of the application are developed for different platforms. The common strategy that are adopted there is that there is a platform specific portion that is abstracted out, and then there is a platform independent portion, and for the platform specific portions different platform modules may have to be developed. Here is an example that will show. So, in the case of an application product line, there can be a platform independent layer, so this could be, for example, business process. Business process is completely independent of the platform on which this runs, or workflow automation. On the other hand, there can be platform specific modules. So, there can be a Linux module, or it does not only have to be an operating system platform, it could be conforming to different databases. So, there can be a database abstraction, and then there can be different databases that is going to sit on top of that, I mean under that. So, for example, it could be Oracle, it could be SQL Server, and so on. So, at this level there could be Linux, Mac OS, and so on. So, the notion is to abstract out the platform independent pieces, and the platform specific pieces you create a single abstraction that is used by the platform independent pieces, and you create the platform specific versions of those. So, here is an abstract interface, this would be an abstract interface. And this abstract interface is used by the platform independent layer, right, and this abstract interface can then take on two different concrete interfaces, or specializations can be done depending on the platform that you go into. Configuration specialization are different versions of the application being considered to handle different peripheral devices. So, for example, there may be a web based system that displays inventory, but the inventory may be gotten off of a RFID system, it could be gotten off of a EPC system, and so on. And so, you may need to have different device drivers to for example, something to talk to an RFID reader, something that can talk to a handheld device that scans UPC codes, and so on and so forth, and all of these are different configurations that you would have to end up creating as you go forward. Finally, functional specialization are the classic example here is that of managing workflow. The workflow could be slightly different in every company, even though all of them do inventory management, although all of them do ERP, the actual business workflow could be slightly different, and that customization is done through functional specialization in this case. So, here is an example of a generic resource management system. We will see the kind of specializations that can occur. The resource management system has several layers. So, it has the resource database at the lowermost layer, then it has the description of resources and the specification of the kinds of reports that it is going to provide, and so on, and it has different interfaces to add resources, delete resources, query the database, browse the database, administration, reporting, etc., etc. And there can be different layers of access at the topmost level, user and programmer access. So, example of a resource management system is an inventory management system. So, in this case, the resource database simply maintains the details of the various inventory that is being managed. The IO descriptions are the structures in the resource database and the input output formats that are used. So, for example, it can be described, I can extract the listing of the inventory in XML, so that it can be passed off to another application. On the other hand, I can extract it in the form of a report that is created into a PDF file, and so on and so forth. The different levels of queries that it provides over this, are there only fixed queries, are there parameterized queries, are there ad hoc queries, and so on, and different access interfaces. So, the key here is the key is modularization. in product lines or in product application families, you have to appropriately modularize everything so that the pieces that can be used or reused across multiple application products are the ones that can be quickly taken and put together, right. So, the separation of concerns to make sure that the appropriate modularization is achieved is very, very important in this case. So, in this case it is also the library system example, in which we have exactly another resource management system, and in this case the library holdings database is the one that is the set of resources. The same set of descriptions are going to be applied, and a set of interfaces or modules are provided. How do you deal with issue, how do you deal with return, how do you generate reports on this, and so on and so forth. The set of users, so user database might have to be created as well in this case, and the appropriate user access, what can you do on the library system is the question. So, so you have seen an inventory management system and a library system. Both of these are resource management systems. Both of these allow you to add resources, query resources, delete resources from the database, get reports on resources, and so on, but both are being used for very different purposes. So, the underlying core of both of these systems could be exactly the same. The notion of maintaining a list of users, giving them access levels, the ability to add a resource, and so on, but the specific database that holds inventory of let us say manufacturing parts versus holding an inventory of books is different. So, the database schema is going to look slightly different, the details of the resource that is being managed is going to look slightly different. So, in the case of family member development, what is done is you elicit the requirements from the stakeholder, and then you choose the closest fit family member that exists. So, there can be several products that have already been built. So, you pick the one that you feel most closely matches the requirements at that point. You may renegotiate the requirements, or you may adapt the existing system, or both could be done in parallel, and then you deliver a new member. So, there is actually an incremental change that takes place to a member of the family that already exists, and that is the key here. So, a large part of the product is being reused, and only an additional small piece is getting done, and that is what is explained in these bullet points. Here is another example of ERP. ERP consists of inventory, sales, purchasing, e-commerce, shipping, etc., etc. So, you can all of these share a common core, right. So, underlying all this, for example, this system was built on top of Apple Web Objects, on top of XML, on top of JMS, etc. All this infrastructure is reused, right. And as you go up, distribution, for example, consists of inventory, sales, purchasing, e-commerce, shipping. Retail consists of other things, and so on. So, that's the notion of product lines. Finally, we'll briefly describe what a design pattern is. A design pattern, the final level of reuse that we talked about, is the notion of reusing design. So, you're not reusing code, you're not reusing product families, you're not reusing architectures, etc. You're reusing designs. And a design pattern is an abstraction of a recurring theme that could exist across multiple systems. A good example of this is something like the observer pattern. In the case of the observer pattern, the problem that is being defined is one where multiple applications exist that may have to observe a change in the data that is going to take place, right. So, an event is going to be passed every time the data is changed, and the applications that are going to observe the change in data are observers, and they take appropriate action on the events. Now, this is a very commonly occurring theme. It could occur in the fact that multiple displays may have to be updated. It could occur in the fact that multiple systems may have to take different kinds of actions on the occurrence of an event, etc. So, why not abstract this out into a design pattern which is described formally using something like UML. So, for example, here is the observer pattern that is described using UML. So, it says there is a subject is the one that is changing, right, and these are all abstract classes. These can be concretized at the appropriate place, right. So, this is an example of design reuse. The notion is being reused. There may not be any code that goes along with it. It just says if you have this particular problem of having multiple observers having to take different actions on a change in one subject, then here is the design you may want to observe, right. So, This is an example of design reuse where the code itself may not get reused, but the notion or the design is getting reused because it is applicable in a wide variety of situations. So, what we have essentially learnt here is two facets of reuse. Reuse itself is pretty critical, it can save a lot of money, but on the other hand you have to be very careful about how you end up employing reuse. Also, designing your applications for them to be reused, designing your components for them to be reused is another aspect of reuse that you have to be aware of, and certain conscious choices and process models would have to be followed in both the cases, designing for reuse and designing with reuse. How do you make a component reusable versus how do you reuse components within building an application. Are some of the techniques and strategies that we have gone through in the course of the last two lectures. And this is something that is obviously a very important facet of software engineering in today's application development.